Okay, so it turns out the Dirac delta function will save us from three things that have seemed really upsetting so far. One is the fact that you guys took a divergence in a curl that ended up being 0, but you don't think it should be 0. So this swirly 1/r function had a vanishing curl, but you didn't think it should on the last homework. And then this in spherical polar coordinates, this 1/r squared also had a vanishing divergence, but it seemed like it was really divergency. So Dirac delta saves us from that too. So this is the physics definition of the Dirac delta function. The Dirac delta function is infinity when x equals a and is 0 when x does not equal a. Okay, never say that to anybody, never talk about that, but that's what should be in the back of your mind. So the really important property of the Dirac delta function is that it's really defined through an integral. So if I have an integral f of x times the Dirac delta function, I get this. So this is the operational definition. So typically Dirac delta functions never hang out by themselves. You see them and they're really only properly defined within the context of an integral. So what this does is it's 0 everywhere. So this is why this is an excellent mnemonic. This is 0 everywhere. And then it's infinity when x equals a. But it's infinity in such a way that the dx, which is 0, you know, like a is just a single point. It has infinitely small measure. It's infinity in such a way that it manages to just pick out f of a. Okay, so this is the formal definition of how you might actually accomplish such a thing. And this comes from the theory of distributions. Technically, what the Dirac delta function is it's the limit in a distribution of functions. And there's actually like kind of a lengthy and I dare say almost like beautiful discussion of all this in Boas's book. It's like 10 pages of just waxing poetic about the Dirac delta function, which I don't know, she like really likes the Dirac delta function. But let me just define this kind of like goofball rectangular pulse. And it has max height k, and then it's symmetrically placed, and it goes in between 1/2k and k, and it's rectangular. So what's true about the area under the curve of this function? So the integral of this is, well, I've got width, this total width is 1/k. And the height is k. So I've made this thing that equals 1. And that's true regardless of what k is. So what happens in the limit that k goes to infinity? Like just picture it in your head. So I kind of cut the width in half, but if I cut the width in half, I double the height. And then I do this again. So I cut the width in half, but then I double the height, and then eventually I get this teeny tiny little skyscraper that has a teeny tiny width, but a preposterous height, and it's always done in such a way that the area equals 1. So this is the theory of distributions definition of, so technically this would be x minus 0, of the Dirac delta function. So it's this thing, but the infinity is chosen in such a way that we get this operational property. So this is, if you, and you can see this two ways, you could take its Fourier transform, or you can just recognize that it's the zero infinity thing that we wanted. So this is the basis function for our Fourier transforms. So integral e to the minus I k1x e to the plus I k2x dx equals delta k1 minus k2. So Dirac delta, not Kronecker delta, Dirac delta. So really long kind of mnemonic of doing this. And that's fine because there's so much more. So here's some properties of Dirac delta. And with this mnemonic in the back of your head where it's the zero infinity thing, this is the thing that's great about it. It's that, it always gives you the right answer. So what is the Dirac delta function of negative x? So let's say I flip it across the y-axis. So I'd hesitate to call it an even function because it's, again, function should always be in quotes. But you can put a negative on the argument, no problem. You get the exact same thing back. So it translates. This is a really cool one. I think I'm going to ask you guys to prove this on the next homework if I remember correctly. Sounds super goofy, but you can define the derivative of the Dirac delta function. Imagine defining the derivative of a function that goes from 0 to infinity instantly and then back to 0. Super cool. So this is true. Any guesses about how you would prove this? And then finally, we have stuffing an entire function inside of the Dirac delta function. So this is also provable and it won't kill you to do so, but it's a little bit more work. So the idea is that Dirac delta blows up at 0, right? And this function g of x might have multiple zeros. So you look for the zeros or the roots of g of x, but as you're doing this, what you get is that you have to divide by the modulus of g at that point. So there's a prefactor that comes out. So these are the really important properties. There are a couple more. So I'll let you guys drink this in for a second, and then we'll just do an example of Dirac delta. And if you get that, you're at least like kind of off and running. I'll show the other two awesome things that it does. Good. Okay. Okay, I'll give you guys a minute to work on that. Everybody get 36? If so, haha, I fooled you. What is this actually? The zero infinity thing is your friend and wants to help you. What are the limits of integration? -3 to 3. Where does the Dirac delta function, quote unquote, blow up? 4. So this is 0 everywhere inside of this interval. So this is 0. Okay, lame trick. I should feel shame, but it's important to note. Okay, what's this? So now I change the limits of integration from 0 to 5. And then we'll do x minus 3 because I already said the answer to the other thing. So what do we get for that? So here I have the Dirac delta blowing up within my limits of integration. So it blows up, quote unquote, at 3, and that's in between 0 and 5. So I just evaluate this. So this is f of x, and this is delta x minus 3 dx. And there's some interval, but 3 lies within the interval, so that's great. So this is f of 3. So I just evaluate that at 3. 3 squared times 2 plus 4 is 22. So that's the beginning primer on Dirac delta. Okay, so now we're going to tell a story about how Dirac delta saves potential theory. And I don't know where, but definitely I think 50% of the homeworks were like, oh, this is, I see what you're trying to do. This is Dirac delta. Okay, we had these two kind of pathologies on the homework, and I'll just call it what it is. There's a vector function b, which is k over r phi hat. And if you looked at it, you're like, what a curly thing, right? And then even when you use the correct curl with all of the scale factors put in properly, what you get is that curl of b vanished. But then in the second part of the problem, you said you were asked to take this integral around a closed loop, so just all the way around at some distance r, it doesn't matter. And this turned out to be not equal to 0. Clearly it's not equal to 0. Everywhere you've got a vector at your back, right? So what happened? Did we break Stokes' theorem, or do I not know how to compute what seems to be like a really obvious curl, or did I write down the wrong form for you guys for the curl in curvilinear coordinates, which is probably the most likely thing? So these are some options. So what is the real answer to this? Is this really zero? So what physical scenario does this B correspond to?
Maybe a magnetic field?
Yeah, a magnetic field created by what?
Some wire.
Yeah, and
Right, with current.
And in an ideal like physics 12, 20 problem set, what's true about this wire, like the first wire you ever seen? It's infinitely thin. So technically what this is was, this actually does have a non-zero thing. So the curl of B should be related to, there's, you know, obviously a physics constant, but it should be equal to the current density. And if I look at this, this is equal to or proportional to the current enclosed, right? So I get a magnetic field with a line integral if I have current enclosed. That's Ampere's law. And then I have Stokes' theorem telling me that I can relate that to the current density. This is an infinitely small current density. So this is actually proportional to the Dirac delta, actually located at, you know, 0. So we'll just call it R equals 0. So we do have current, we just have an infinitely small current, and that just wouldn't show up unless we knew there was a Dirac delta function at the origin. Likewise, we had this other pathological example. We had, we'll call it what it is, an E, and E looked like K over R squared, and it pointed in the radial direction. And clearly E is a really super divergency thing, but when you guys calculated the divergence in spherical polar coordinates using the correct formula, what you got is that this thing disappeared, because when you multiply by the R squared, you know, like just magically everything disappears. And this was upsetting, because when you took the other side of this and you asked how many field lines pierce through a surface, closed surface, which is Gauss's theorem or the divergence theorem, obviously there are field lines that pierce the surface. So integral E dot ds equals not 0, should be equal to the current enclosed. But what is it that is making this field? So this particular field. This is the electric field due to what type of charge? So first electric charge you ever learned about is a point charge located at the origin. So we didn't break the divergence theorem. We just forgot to include the infinitesimally small, in this case, charge and current located at the center. And so now that we have the Dirac delta function, this is how we would write that correctly. So this is really what's going on. So we can represent point charges and point currents. So I have a point charge of charge Q. It's located at the origin, so it's Dirac delta. And over E naught is the right way of writing this. Divergence of E is rho over epsilon naught. Our current density, or sorry, our charge density is infinitely big at the origin, and it's 0 everywhere else. That is a job for the Dirac delta function. So likewise, when we look at the current density in a magnetic field, this is mu naught, whatever that current is, delta R, right? Oops, sorry, it's curl. And that's mu naught J enclosed. So this is the current density. Probably didn't spend too much time there. So the Dirac delta function is 0 and it's infinity when it needs to be. If you're thinking about a point charge, for instance, it really is infinitely dense at the one point where you look at point charge. And it kind of makes you wonder, like, if point charges really existed, would we have black holes everywhere? Because that's an infinite amount of mass at a point, but it's good enough. There's a pretentious way of writing this. This is Dirac delta function is 0, either AE in English or PP in French, almost everywhere, or presque partout. But 0 infinity. And it saved us in these two places where on the last homework it seemed like we actually broke two important integral calculus theorems. Any questions about that? Okay. I will give you guys the briefest intro to tensors because I think it's like 15 minutes, and you can just kind of I'll review, I think, some of this stuff on a separate video, but you can let this kind of like wash over you like a Wagner opera or something.